Today we will study the invariance of the electric charge and the covariance of the electrodynamics. Basically, we will see that the covariant forms of the Maxwell's equations and the gauges, wave equations. So let us start with the constant. So we have seen that the speed of light is constant in all frames. Another invariant quantity is the electric charge. So electric charge observationally is the same in all frames. The minimum of the charge is the proton or electron, and the actual charge of any atom is the multiples of the electron charge or proton charge. So experimentally, the difference between the electric charge and the proton charge at the order of 10 to the minus 19, and for the relativistic speeds it is seen that the charge is the same up to the speeds of 0.4 c, speed of light. So we have two constants, speed of light and the electric charge. So last time we have seen that for momentum, so time coordinate was corresponding to energy over c, and space part is the p. So that was equal to mass times mu 0 mu, mass times 4 velocity, and the 4 velocity is nothing but with respect to, we write this with respect to the proper time, that is equal to gamma c, gamma v. P0 is the energy, time coordinate. And let us start with the Lorentz force. So can we write the derivative of this for momentum? Yes, we can take the derivative. And we can look at which term is corresponding to which term of the Lorentz force in 4 dimension. So very simply, the Lorentz force, rate of change of the momentum in time, is equal to Q times electric field plus V cross B over C in Gaussian units. So we are now switched to the Gaussian units. So in the new chapter we will use that the Gaussian unit. Up to now we use the standard units, but I know that you learned to switch the standard units to the Gaussian units in the first part of the course. So this is the Lorentz force with respect to the time, but we are not happy with the time because the time is different in different coordinate systems. We have a universal scaling, that is the proper time, d tau, and that is dt over Lorentz factor. So this proper time is same, everybody agrees that that is the same everywhere. So you can use that the proper time, or you can multiply with speed of light, you can say that as a proper length. So if you take this instead of dt, if you write gamma tau, the expression turns to be derivative of the momentum with respect to the proper time, which is equal to Q gamma E gamma V cross B over C. So actually we pick up a term gamma V. Gamma V is the proper velocity, space part of the proper velocity. If I multiply by C, divide by C, the first term will be the time coordinate of the for velocity. So basically this will be mu0, this one. So time coordinate of the for velocity, and gamma v will be u. And what we obtain here, the Lorentz force with respect to the invariant time, which is the proper time, is equal to, take the c out of the parentheses, q over c u0 e plus u cross b. So this is the part of the for momentum space part of this. So this is 3 in 3 dimensions, so px, py, pz. And what about the time coordinate or the first coordinate of the for momentum? So basically p0 is e over c, and if you write the differential form and to take the derivative with respect to the proper time, this will be what? That will be 1 over c dE over d tau. So this is the derivative of the time coordinate of the for momentum, e over c, and if you take the write in the differential form, and then you will obtain that the time coordinate of the for momentum with respect to the derivative of the proper time in that form. So let us keep the left hand side dp0 over d tau, and for the right hand side say that try to express something we know. So you can write this as a dE over d tau. D tau is dt over gamma. So gamma goes up, and that is gamma over c dE over dt. And what is the dE over dt? So dE over dt is, what is the dE over dt? The rate of change of the energy. Rate of change of the energy is nothing but q over gamma over c QE dot V. So what is the QE? QE is the force dot V. So that is the power. So that E is the electric field, or you can write this in the following form. You can write this in the following form. dE is nothing but Q dE dot dx. So if you have a Lorentz force, and if you take the scalar product with the displacement, only work done on the system will be the electric field, magnetic force V cross B dot dx will be the 0, because dx and V are parallel to each other. So magnetic force does not do any work. So V cross B dot dx will be 0. So if you write this, so the other term will be Q over C V cross B dot dx, and this term will be the 0. V and dx parallel to each other, so all the times that product is 0. So basically work done on the system will be the Lorentz force dot product with the displacement. So instead of Q, you can write dE dot dx, and if you take the time derivative of dx over dt will be the velocity, and you can obtain that the dp0 over d tau, time derivative of the time coordinate of the 4 momentum will be what? Will be QE dot V gamma over C, and I know that gamma times V is nothing but the U, space part of the 4 velocity taken with respect to the proper time. So that is nothing but Q over C electric field dot gamma V, and that is equal to dp0 over d tau q over c dot u. So we have at hand the 4-dimensional Lorentz force. The time coordinate of the 4-dimensional Lorentz force dp0 over d tau is nothing but the power, energy generation, power rate, energy rate or power, Q over C E dot U, and space part of the 4-dimensional Lorentz force dp over d tau, and that is equal to Q over C U0 E plus U cross B. So this is the form, and Q is invariant, C is invariant. We have 4 velocity piece of the, but we don't know what we can say for the electric field and the magnetic field, because we haven't studied that the properties of the Lorentz transformations of the electric and magnetic field. The question, can we write this in the covariant form? Yes, we will write, but we have to know first what kind of transformation rules we have for the electric field and the magnetic field. What is the field strength tensor? So let us leave it this 4-dimensional Lorentz force there, and let us investigate what else we have in the covariant forms in electrodynamics. So one of the equation, very important equation, is the charge density. So continuity of the charge density tells you that change in the charge density in the time plus divergence of J is equal to 0. The integral form of this more understandable. If you take the volume integral of this will be what? Total charge, and that will be the derivative of the total charge with respect to the time, or decrease of the total charge in time. And if you take the volume integral of the divergence of J from the divergence theorem, that turns to be J dot current density over the closed surface, and that tells you that if there is a decrease in the total charge in time, there should be a current flux through the closed surface. So if there is a charge here, if it is replacing if it is changing, if there is a total charge there, Q, if the charge is decreasing in time, and there should be a current flux through the closed surface. So in other words, if there is an electron or proton here in this classroom, and that could go to the Mars or Venus, whatever, by passing a closed surface here. So as a current it can go. It cannot disappear here and appear in Mars or Venus elsewhere. So there should be a current. So this is the continuity equation, conservation of charge density. So can we have seen last time that the covariant form of the continuity equation. So if you remember, I derived that del alpha, let's say a alpha, which is equal to del alpha a alpha for all coordinates. It doesn't matter. So the continuity equation was in covariant form in all coordinates. I derived this using the covariant and contravariant transformations of the four-dimensional derivative operator and the first rank or vector, and I find that they are the same in all frames. So if you say this is prime, this is unprime, if they are Lorentz or inertial frames, the form of the equations are the same. So can we write this is in continuity equation using the current density? Yes, we have to define a four-dimensional current density. So alpha is 0, 1, 2, 3, and if we call that the time coordinate of the four current density is charge density, and the rest is the ordinary current density, we can have some form of the four-dimensional current density. And the next, does it satisfying the continuity equation? Let us look at. So the situation is the following: when the index is up and when the index is down, so one is contravariant, the other is covariant. So this is nothing but del over del x0 plus a gradient, and for the other one, for the contravariant current density, this is nothing but C rho times current density. So x0 is Ct, and if you take this divergence, what you are going to obtain? Del rho over del t, c's will be cancelled, plus divergence of j, and that is nothing but the continuity equation, and that is equal to 0. So basically, this is the covariant form of the continuity equation, charge continuity equation, and this is the same in all Lorentz frames. So we have seen that the charge density, conservation of the charge density is covariant in all frames. The form doesn't change in all frames. So the other thing, what are the other invariants? I said to you that the charge. So the charge is invariant in all frames, and the same. Basically, if you look at the total charge, let's say in this cubic box, that will be charge density times d cube x. D cube x is just the x, y, z coordinates. And if you look at this, another frame moving some velocity k prime, and then what will be changed? The total amount of the charge have to be conserved because the q is conserved. So what will happen? If you look at this from a moving frame, then you will have new volume that will be contracted, and you have new charge density, but you have the new volume density. And what we know that the total charge in this box doesn't change. That means that the charge density times d cube x prime is equal to charge density times d cube x. So one is seen in the one inertial frame, in Lorentz frame. You are seeing that the charge density is changed, but the volume element is changed. And in the other frame, you are seeing that the charge density is rho and the volume element is d cube x, but the total charge is conserved. But actually, this is for 3 dimension. We are working in 4 dimension. And in 4 dimension, we can say that d to the 4. d to the 4 is nothing but dx0 times d cube x. dx0 is the time coordinate and d cube x is the space part. And what about this? We know that this is obeying the Lorentz transformation rules. So if you use that the Lorentz transformation, that will be d to the 4 x prime in the new frame. And that transformation is, that relation between these two is the relation of the Jacobians. So if you write in the Jacobian in general as a del x prime 0, del x prime 1, del x prime 2, del x prime 3 over del x 0, del x1, del x2, del x3. So you can write this a 4 by 4 matrix, and you can calculate the Jacobian using the determinant. And this is nothing but this is nothing but a determinant of the 4-dimensional boost matrix. If we have a boost, if the frames are boosting in 3 dimension in space, and then that determinant A is equal to 1. This is for proper Lorentz transformation. The bottom line is the following: d to the 4 x prime and d to the 4 x is the same. So 4-dimensional, let's say, volume element in space-time is the same in all frames. So this will be quite helpful when we write it the action for the Lagrangian density. Now, let us write this somewhere else. So 4-dimensional volume element is the same in all Lorentz frames. We have the continuity equation, continuity of the charge density in all frames is valid, and we have the 4-dimensional current density. Time coordinate of the 4-dimensional current density is the charge density, and the space part of the 4-dimensional current density is the actual current density in space. So let us look at the Lorentz condition. So what is the Lorentz condition? 1 over c del phi over del t, divergence of A is the Lorentz condition. And under this condition, you know that the equations representing the Maxwell's equations in terms of the scalar and vector potentials decouples as a non-homogeneous wave equation that is equal to 1 over c square del square A over del t square minus Laplacian of A is equal to 4 pi over c times the current density, and the other is 1 over c square del square scalar potential over del t square minus Laplacian of scalar potential is equal to 4 pi times the charge density. And this is for I am using the Gaussian units. And can we define another 4-dimensional quantity? So if you make a comparison with this equation and that equation, they are in the similar form. So if you want to define a 4-dimensional potential, that is very simple. So you can write that the 4-dimensional potential A alpha is scalar potential which is corresponding to time coordinate, and for the space coordinate the ordinary vector potential which we know. So if you say that our vector potential in that form, you can automatically see that the del alpha A alpha is nothing but the Lorentz condition. So let us call this is Lorentz condition, and under these conditions we know that our equations representing the Maxwell's equations, vector potentials and scalar potentials, they are decoupled. That is very important. Lorentz conditions is important. And if we know that if we have a non-homogeneous wave equation with source, current density and charge density, we know that how to solve. We have the tool of the Green's function, and we can solve the vector and scalar potentials very easily. And this tells us that the Lorentz condition is satisfied in all frames. So that is the same structure, del over C times del over del T plus a gradient. This is the 4-dimensional covariant derivative operator, and this is the 4-dimensional contravariant indexes up for potential. If you act this, what will happen? You will take the derivative of the scalar with respect to del over del T, 1 over C, and the plus divergence of A, or del over del X over del X, del over del Y over del Y, and so on. So this is nothing but the Lorentz condition. And as we said that this is in covariant. In all frames they are the same. The form doesn't change. So next thing, we learned that the 4-dimensional potential. We learned that the 4-dimensional current density. Now we learned that the 4-dimensional current density, and that is automatically satisfying the Lorentz condition in all frames. And what else? Now we have two inhomogeneous wave equations. So how we can we express this as a covariant form? Yes, we can. We have another tool. What is that tool? 4-dimensional Laplacian operator is del alpha. Del alpha is, if you act a function, is covariant in every frame. The open form is del square over C square del T square minus Laplacian. And what else? On the left hand side of that, we have charge density and current density. Charge density and current density is the 4 current density. And what is the scalar potential and vector potential? That is another for vector for potential. So you can write that this set of inhomogeneous wave equations. How many inhomogeneous wave equations? You have 3 here, 1 there. So you can write in that form. 4-dimensional Laplacian operator acting the 4 vector should be equal to 4 pi over C j alpha. So these are the wave equations, non-homogeneous wave equations for the Lorentz conditions. So if you look at this, for example, if you say that, what is this? This is equal to del square over c square del t square minus Laplacian. If you say alpha is equal to, by the way, let me write, alpha is 0, 1, 2, 3 on all cases. If you say for alpha, if you write this for alpha is equal to 0, that is equal to alpha 0 is the scalar potential, that is equal to 4 pi over c j0. Where is the j0? The j0 is the c times rho, and c's will be cancelled, and which equation we will obtain? You will obtain 1 over c square del square over del t square acting to scalar potential minus Laplacian acting to scalar potential is equal to 4 pi times the charge density. And if you work on for the x component, you will find that the non-homogeneous wave equation for the x component of this. If you work on for y component, you will get another equation, and for z again, you will obtain 4 sets of independent non-homogeneous wave equations, and this is again a covariant. In all frames, they are the same. If you work on this frame, or if you work on different frame, the form doesn't change. So these are the covariant forms of the continuity equation, Lorentz condition, and non-homogeneous wave equations. So let me collect these things here, and let us continue to work. So we have what? We have here another equation that is Lorentz condition, and another one is charge density continuity equation. So that is del alpha j alpha is equal to 0. So this is again Lorentz condition. So where are the 4 vectors? J alpha is 0, time coordinate is 0, space coordinate is the current density, and 4 potential A alpha, time coordinate of the 4 potential is the scalar potential, and the other is the vector potential. So what is left? Maxwell's equations. So let us write the for example the electric field in terms of potential. So the electric field in terms of the potential is equal to 1 over c del E over del T minus gradient of the scalar potential, and the magnetic field is the curl of E. So which equations we use to derive this? This is from del dot B equal to 0, and the above was from the Faraday's law. Curl of E plus del B over del T is equal to 0. That is the consequence of the fields deduced from the 2 homogeneous Maxwell's equations. Del dot B equal to 0, curl of E plus del B over del T is equal to 0. One of them is there is no magnetic monopoles. The name of the other one is the Faraday's equations. So let us investigate this one. So let us write for just x component. And if you write this just for x component, you will obtain minus 1 over c del Ex over del T del phi over del x. Now, can we express these things in terms of four potential and four derivative operator? Yes, we can do. So we can, let us write del alpha when the index is up, that is equal to del over del x0 minus a gradient. And when the index is down in the covariant form, this is del over del x0 plus gradient. So Ex on the left, on the right. What? So x is the x component. Instead of del over c del t, what you can write? What is the del over del ct? What is this? This or that? That is nothing but del x0. So let me write in this form, minus del 0. How about a1? Ax. Ax is nothing but a1. So is it in the correct sign? So let me take this in this parenthesis. So if you ignore this term in a moment, so that will be what? Del of 0 will be del over del ct, and a1 is nothing but ax minus, what is the del over del x? Del over del x is del 1. What is the phi? Phi is nothing but time component of the four potential, that is a0. So we find something there. So this term is positive, del over del 0 is positive, a1 is positive, multiplied by minus, that will be minus. How about this, the second one? Del over del 1, this is the up index, so that is the contravariant, so that is nothing but negative, negative del over del x, and a0 is positive, so minus is positive, and there is one more minus that makes this as a negative. So above and below are the same. So what we use that the elements of the four derivative and four-dimensional derivative, partial derivative operator, and four-dimensional potential. So let us work on another quantity, for example bx. If you work on with the other quantity bx, so bx is equal to del ez over del y minus del ey over del z. So can we write this in terms of components of the four-dimensional partial derivative operator and the four-dimensional potential? So tell me now, what is del over del y? Which one is del over del y from here? Which one? So del 0, del 1, del 2, del 3, which one corresponds to the del over del y? Del 2. So del 2. So that is del 2. Which one corresponds to the AZ? Which one corresponds? A3. So now whether the sign is correct or not, in this is up. So when this index is up, contravariant, that should be negative. Okay? Therefore, I need another negative here to make a positive. Now, and here you have a minus sign. And what is del over del z? Del 3. And what is EY? 8, 2. So again, minus and minus is plus, but del 3 is negative. That makes negative, and A2 is positive. So the situation is the following. You can generate the elements of electric fields, components of the electric field and magnetic field in a pattern of the following form in general. Del alpha, A beta, del beta, A alpha, and alpha 0, 1, 2, 3, beta is 0, 1, 2, 3. And this is called as a field strength tensor. It is second rank because in each value of alpha and beta you have the quantities. Those quantities are the x, y, z components of the electric fields and the magnetic fields. So this is called as a field strength tensor. So the elements of the field strength tensor is the following. If you write this in 4 by 4, the situation is the following. 0, 0, if you put 0, 0 here, that is 0, all diagonals are 0. And if you look at this, what is the 0, 1? 0, 1 is nothing but this 0, 1 minus 0, that is equal to minus EX component. If you do this for 0, 2, that is minus EY, and for 0, 3, that is minus EZ. And if you change the alpha and beta, what is changed? If you change the alpha and beta, what is changed from here? You are seeing. If you change it instead of alpha, say beta, instead of beta, alpha, what will be changed? There will be a minus sign. So it's an antisymmetric tensor. So basically 0, 0, 0, 1, 0 to 0, 3 is antisymmetric to 1, 0, 2, 0, 3, 0. All diagonals are 0 because it's an anti-symmetric matrix. Otherwise, it doesn't. And this is minus BZ, BY. So if you write this cell by cell, and that is equal to minus BX, and this is symmetric part of this, that is plus BZ, and this is the symmetric part of this antisymmetric part, so sorry, that is plus bx, and this should be minus of this minus by. So if you do one by one, say 0, 1, 0, 2, 0, 3, or 2, 0, or 2, 2, whatever, you will find that the elements of the fields, and it's a second rank tensor, and it's an antisymmetric tensor, and you can derive the all elements. So that is anti-symmetric through the diagonal. All diagonals are 0. So minus bz. So these are the diagonal terms. So if this is just a reflection, so minus e plus e, minus ey plus ey, minus ez plus ez, minus bz plus bz, plus by minus by, minus bx plus bx. So now what will happen? We will write the Maxwell's equations using this field strength tensor, and we will write it the 4-dimensional Lorentz force using the Maxwell field strength tensor and the 4 velocity in the next R. So I have to show you a few more tools before the break. You know that you can lower the indices up and down using the metric tensor. Some of the results you have to know that. So if you have a indices up, let's say gamma and delta, and if you want to lower these indices down as a covariant, let's say alpha beta, you need a metric tensor. So if it is gamma, it will end up with beta. Sorry, if it is delta, it will end up with beta, and if it is gamma, it will end up with alpha in the choice. So you can lower the indices by contracting the gamma component and leaving this as a beta. So if you sum up these or contract these deltas, it will leave the beta as a free index. And similarly, for that one, you have the gamma and you need a free index alpha. If you contract these two, you will obtain the alpha beta in the free index, and that will be in the down indices. So using the metric tensor, you can change the places up index or down index easily. So that is the only tool we can use. So gamma and gamma is contracted. So delta and delta is contracted, and gamma is contracted, and left a free indices of the field strength tensor as alpha beta. But if you do this, some of the forms of the field strength tensor you have to know. So if you do this, you will obtain the following. So f alpha beta will be the following: 0 ex ey ez, and in the first column minus ex minus ey minus ez. So divide this to the again as cells, and replace everything. All diagonals will be 0. It's anti-symmetric matrix, and this will be minus bz, and this is by, and that is minus bx, and this is the reflection with the minus sign with the diagonal, so that is Bz, and that is minus By. This is minus Bx, that should be plus Bx. What is changed between the F alpha beta up and the F alpha beta down? What is the change practically if you look at this? Are the B components change? No. What happens to the E fields? Only sign is changed. So if you have a passage from contravariant to the covariant form of this, in that passage E goes to minus E. So E is take the negative sign. So in the next hour, I will show you that another tensor, that is the dual field strength tensor. We will construct this as another tool, 4-dimensional tensor we will use, and using this we will generate a dual field strength tensor, and with these tools we can write the Maxwell's equations in the covariant forms. So let us give a break.